Welcome back, everybody. Learning is a hobby here. Want to finally finish the exercise set for chapter 8 in this video. So this is part 2 of the exercise set for chapter 8. Now, once I finish this video, I'm not actually finished with chapter 8 because I still have to do the appendix to chapter 8, which is on uniform continuity, and then it has its own exercise set. But I should hopefully get those done by the end of the weekend. So that once that's done, we'll be done with chapter 8. But if you watched my vlog, you know that there's still some stuff we got to do before we move on to part 3 of the book. So, but let's this video is about the rest of the exercise sets from chapter 8. So let's do that right now. Let me bring up my solutions. All right, and we'll go through them. Okay, so starting with question number 14, which is where we left off in part 1. Okay, I mentioned this before in the part 1 for this exercise set, that a lot of these problems introduce concepts that are important, which is why I want to do as many of them as I've done so far. So I basically did all the problems from 14 onward. So there's like 6 problems that we'll do in this video, which is I basically did almost every single problem in chapter 8. But anyway, 14a says this: consider a sequence of closed intervals, and he's defining how we're going to make them here. So I1 is the closed interval from A1 to from A1 to B1. The interval I2 is the closed interval from A2 to B2, and so on like that. Suppose that AN is less than or equal to AN plus 1, and BN plus 1 is less than or equal to BN for all n. So in other words, the lower endpoints are an increasing sequence, and the upper endpoints are a decreasing sequence. Okay, and he says see figure 8. Actually, let me show you what the picture looks like for that on the textbook here. So this is figure 8, so you can see what the intervals look like. So this is this interval here is I1. This interval here is I2. Oops, I2. This is I3, etc., etc. Okay. Okay. And then he wants us to prove that there's a point X which is in every IN. All right, so here we go. So by problem 12, if you don't remember, we did problem 12 in part 1, so you could look at that if you want to, but I'll just remind you of what question 12 said. In question 12, if you look at part B, well, let's read part A and part B. Suppose A and B are two non-empty sets of numbers such that X is less than or equal to Y for all X in A and all Y in B. Then part A says prove that sup A is less than or equal to Y for all Y in B. And part B said prove that sup A is less than or equal to inf B. So we're going to use that result to do this, this problem here. So by problem 12, S equals the supremum of the sequence of ANs, which is less than or equal to the infimum of the sequence of BNs, which I'm calling I. So S is the supremum of the ANs, and I is the infimum of the BNs. So that relationship is follows just from problem 12, right? And then define I to be the intersection of all of the intervals IN. Then if S is equal to I, then AN is less than or equal to S is equal to I less than or equal to BN for all natural numbers N. Therefore, S is in IN for all N in all natural numbers N, which implies that S is in the intersection of all the INs. If S is less than I, then there's a rational number R such that S is less than R less than I. That's by the density of the rationals in the real numbers. And that implies that AN is less than R less than BN for all natural numbers N. So R is in IN for all natural numbers N, which implies that R is in the intersection of all of the intervals. Okay, that's the proof for part A. And then part B says, Show that this conclusion is false if we consider open intervals instead of closed intervals. So I came up with a counter example here. Excuse me. Consider the sequence of nested intervals in, defined to be the open interval from 0 to 1 over n for all natural numbers n. Assume for the sake of contradiction that there is an x in the intersection of all those intervals, then x would have to be greater than 0. Furthermore, we can find a natural number n so large such that 1 over n is less than x. That's by the Archimedean property. Therefore, x is not in ik for any k greater than or equal to n, which contradicts that x is in the intersection. So that means that the intersection has to be empty. Right? And then he has a note here. This is actually an important theorem in analysis. This is called the nested interval theorem. It may be used to give alternate proofs of theorems 1 and 2, which we'll actually do in a second. The appropriate reasoning outlined in the next two problems illustrates a general method called a bisection argument. So we're going to prove theorem 1 and theorem 2 using a bisection argument in question 15 and question 16. All right, so here's question 15. Suppose f is continuous on the closed interval from a to b, and f of a is less than 0 is less than f of b, then either f of a plus b over 2 is 0, or f has different signs at the endpoints of the interval, the closed interval from a to a plus b over 2, or f has different signs at the endpoints of the closed interval from a plus b over 2 to b. He says why? Well, if a and a plus b over 2 have the same signs, since a is negative and b sorry, if since f of a is negative and f of b is positive, then obviously it changes sign over the other interval, right? And vice versa. So if f of a plus b over 2 is not 0, let I1 be the interval on which f changes sign. Now bisect I1. Either f is 0 at the midpoint or f changes sign on one of the two intervals. Let I2 be that interval. Continue in this way to define in for each n unless f is 0 at some midpoint. Use the nested interval theorem to find a point x where f of x equals 0. So here's my proof. He pretty much tells you how to do it in the question, but here's my proof. So construct the sequence of intervals in as outlined above. Then in plus 1 is contained in in for all natural numbers n. So in other words, you get a nested sequence of intervals, right? Therefore, the intersection is not empty by the nested interval theorem. Furthermore, the length of the nth interval is b minus a over 2 to the n, because we keep having the lengths of the intervals, right? That means that the length of the intersection of all the INs is the limit as n goes to infinity of b minus a over 2n, which is equal to 0. That implies that the intersection has to contain a single point, right? If none of the midpoints, that follows if none of the midpoints are roots of f. If they are, then you're done, right? So here I'm just assuming that none of the midpoints are roots of f. Since f is continuous on the closed interval from a to b and x is in the closed interval from a to b, f of x is greater than 0 or f of x is less than 0 implies that there's a delta greater than 0, such that for all y in the interval, the open interval from x minus delta to x plus delta, f of y is greater than 0 or f of y is less than 0 respectively. However, we can find a natural number n such that b minus a over 2 to the n less than delta. Again, that just follows by the Archimedean property of the real numbers, and therefore f changes sign at the endpoints of in, and in is a proper subset of the open interval from x minus delta to x plus delta. This is a contradiction, therefore f of x has to be 0. Okay. Right, so that's the proof of theorem 1 using the nested interval theorem. Question 16 is the proof of theorem 2, but theorem 1 and theorem 2 that I'm referring to are the theorems from chapter 7, by the way. So here's question 16. Suppose f were continuous on the closed interval from a to b, but not bounded on the closed interval from a to b, then f would be unbounded on either the closed interval from a to a plus b over 2, or the closed interval from a plus b over 2 to b. He asks why. Well, if it's unbounded, it has to be unbounded on one of those intervals or the other one, right? It could be unbounded on both, but like at least one of them has to contain a point where the function is unbounded. Okay, let I1 be one of these intervals on which f is unbounded. Proceed as in problem 15 to obtain a contradiction. So here's my proof. Again, he pretty much, tells you really what to do. So, but here we go. Construct a sequence of intervals in as instructed. Then the intersection of the INs contains just the point x, again by the same reasoning as I showed in question 15. Then f is continuous at f continuous at x implies f of x is defined. It's a real number, right? Furthermore, by continuity, for epsilon greater than 0, there is a delta greater than 0 such that f of y is bounded. Further by continuity. Sorry, this should have been infinity. This is fine. What I mean is it's finite. That's a typo. Let me just fix that. Sorry, that should be infinity there. So furthermore, by continuity, for epsilon greater than 0, there's a delta greater than 0, such that all of the f of y's are bounded in magnitude for all y in the interval from x minus delta to x plus delta. In fact, there is a natural number, n, which I'm calling n star, such that b minus a over 2 to the n star is less than delta. Then f is bounded on the interval I sub n star. That's a proper subset of the open interval from x minus delta to x plus delta, which contradicts that f is unbounded on in. Therefore, f is bounded on the closed interval from a to b, and that's the proof. All right, so that's the proof of theorem 2 using the nested interval theorem. And actually, there should be in star here as well. Okay, going on to question 17. We're going to use something like this when we get to the Dedekind cuts later on down the line. But let's prove these things right now. So 17 has a few parts. Part A says let A be the set of all x that are less, where x is less than some alpha. Prove the following. He says in the problem, he says these are all easy. So, and they are, but let's do them. So property 1 says if x is in A and y is less than x, then y is in A. So here's my proof. Let x be an element of A and y less than x, then y less than x less than alpha implies y is less than alpha, which means that y is an element of A. Okay, that's the proof. Property 2 says A is not empty. So here's my proof. If alpha is in R, then alpha minus 1 is also a real number, and alpha minus 1 clearly is less than alpha. Therefore, alpha minus 1 is in A. Therefore, A is not empty. It has something in it. Right, property 3 says that A is not the entire set of real numbers. So here's my proof. Alpha is an element of R, and alpha, excuse me, and alpha is not in A, since alpha is greater than or equal to alpha. Therefore, therefore A is not the entire set of real numbers because alpha is not in the set A. Excuse me, I don't know why I got like a scratchy throat here. Okay, property 4, if x is in the set A, then there's some number x prime in A such that x is less than x prime. So here's my proof. Let x be an element of A, then obviously x is less than alpha. By the density of the rationals in R, there's some rational number R in Q such that x is less than R is less than alpha, and that implies that R is in A. That's it. Okay, and then part B says, suppose conversely that A satisfies properties 1 through 4, and that we want to use that to prove that the set A is equal to the set of all x, such that x is less than sup A, so the supremum of A. So here's my proof. So A not empty, that's one of the properties, so we're allowed to assume that. A not empty implies there's an x in A. Assume for the sake of contradiction that A is not bounded above. Then for any y in the real numbers, there is an x in A where y is less than x, which implies that y is in A. That implies that A is a subset of R and R is a subset of A, which implies that A equals the real numbers, but that contradicts one of the properties. Therefore, A is bounded above. Okay, and that means that sup A exists. So sup A is a real number. Then for any x in A, x is less than or equal to sup A just by the definition of least upper bound. Furthermore, x is not equal to sup A, since if it was, then there would be an x prime in A such that sup A is less than x prime, contradicting that sup A is the least upper bound of A. Therefore, A has to be a subset of the set of all x such that x is less than supremum A. Right? If x is in the set of all x such that x is less than sup A, then there's an x prime in A such that x is less than x prime, which implies that x is in A. Therefore, the set of x such that x is less than sup A is a subset of A. Therefore, A is equal to that set. Right? If they're both subsets of each other, then they have to be the same set. Okay. Question number 18. A number x is called an almost upper bound for A if there are only finitely many numbers y in A with y greater than or equal to x. An almost lower bound is defined similarly. So there's a bunch of parts to this one as well. Part A says find all almost upper bounds and almost lower bounds of the sets in problem one. Problem one is one of the ones that I didn't do on the video. So I wrote the sets down again here, and I'll just give you the answers. I don't want to. I guess I won't really like go through. I mean, there's nothing really much to say. These are the sets of all almost upper bounds. So for this first set, the set of all almost upper bounds is the open interval from 0 to infinity, and almost lower bounds is the set from negative infinity to 0. Here we include 0. Um, I don't know how much to say about how much maybe I should just scroll through it and you could see what the answers are, and then because I think the next part is a proof. These are the answers for these sets. You can find them yourself. It's relatively straightforward. Right. Part B says, suppose that A is a bounded infinite set. Prove that the set B of all almost upper bounds of A is non-empty and bounded below. So here's the proof. Since A is bounded, it's bounded above, right? Bounded means bounded above and bounded below. So if it's bounded, it's bounded above. Therefore, A has a least upper bound, which I'm calling S. So that's the supremum of S is the supremum of A. Then A intersect the interval from S to infinity, where S is included, is just S, contains just S, or it's empty. Therefore, S is in the set B. Also, A bounded implies that A is bounded below, and therefore has greatest lower bound, which I'm calling L. So L here is the infimum of A. Since L is less than or equal to A for all A in A, and A is infinite, L is not an element of B, and L is less than or equal to B for all B in B. Since B is the set of all almost upper bounds for A, therefore B is bounded below. And that's the proof. And C and D, again, he's just asking us to find these numbers. I'm not going to really belabor it, but I do want to talk about this definition here just so you know what it means. It follows from part B that inf B exists. This number is called the limit superior of A and denoted by limit with like about a bar on top of A, or it's sometimes referred to as lim sup of A, which is that's how I'll refer to it, lim sup. It means limit superior. Find lim sup of A for each set A in problem one. So again, I'll just show you my answers here, and then I want to get to the ones that are involve proofs. So these are the limit superiors for each of these sets. All right. Part B, define. This is lim inf. It's pronounced. It's the limit inferior of the set A. So define it and find it for all A in problem one. So here's my definition. Let L be the set of all almost lower bounds for A. Then lim inf of A is equal to sup L, the supremum of L. And again, just saying here, this is sometimes written lim inf. It stands for limit inferior, right? And again, here the limit, the lim sorry, it's hard to say, lim infs for the sets in part A. Again, you could figure this out yourself. They're straightforward. So I wanted to show you that mainly just for the definitions, and so that we can do problem 19 here. So if A is a bounded infinite set, then there's a bunch of things that we want to prove for lim inf and lim sup. All right, so part A says show that lim inf of A is less than or equal to lim sup of A. So here's my proof. Let L and U be the sets of all almost lower bounds and almost upper bounds of A. Then for any L in L and U in U, L is less than or equal to U. Therefore, sup L is less than or equal to inf U by problem 12. It just follows from problem 12 in the definition. Right, part B, they want us to show that lim sup of A is less than or equal to sup A. So here's my proof. Let U be the set of all almost upper bounds of A, then sup A is an element of U, which implies that inf U is less than or equal to sup A. Just pretty much follows some definitions. Part C, if lim sup of A is less than sup A, then A contains a largest element. So here's my proof. Assume lim sup is less than sup A, then there's a rational number R in the there's a rational number R in the open interval from lim sup of A to sup A, then R is an almost upper bound for A, then there are only finitely many elements of A in the interval R to sup A. Say that those finite elements are A1 up to AN, then the maximum of that set is the largest element of A. Right, and then in part D, he wants us to do parts B and C again, but for lim inf. So here, he wants us to prove the analogs of part B and C for lim inf. So here we go. So for part one, we want to show that inf A is less than or equal to lim inf of A. So here's my proof. Let L be the set of almost lower bounds of A, then inf A is an element of L, which implies that inf A is less than or equal to sup L, which is equal to lim inf of A. And that's the proof. Part two, assume part two, this is the proposition. Inf A is less than lim inf of A, implies A contains a least element. So here's my proof. Assume inf A less than lim inf of A, then there's a rational number R in the open interval from inf A to lim inf A, and the intersection of A with the interval inf A to R contains finitely many elements of A, since R is an almost lower bound for A, and say that those elements are alpha 1 to alpha n, then the minimum of those elements is the smallest element of A, and that shows that A has a minimum element, or a least element. Okay, last question is number 20. Let f be a continuous function on R. A point x is called a shadow point of f if there's a number y greater than x with f of y greater than f of x. The rationale for this terminology is indicated in figure 9. Let me just show you figure 9, so you can see what he's talking about. All right, this is figure 9. So he's going to explain what all these things mean in a second. So the parallel lines are rays of the sun rising in the east, and he says in parentheses here, you are facing north. Suppose that all points of the open interval from A to B are shadow points, but that A and B are not shadow points. Clearly, f of A is greater than or equal to f of B. Okay, so again, just going back to the picture so you can see. So here, if this is the interval from A to B over here, then all of these points are shadow points. All right, here's part A. Suppose that f of A is greater than f of B. Show that the point where f takes on its maximum value on the closed interval from A to B must be A. So here's my proof. Let each point x in the open interval from A to B be a shadow point of f, but A and B are not shadow points. Assume that f of A is strictly greater than f of B. Since f is continuous on the real numbers, f is continuous on the closed interval from A to B, and therefore f takes on its maximum value in the closed interval from A to B. That's one of the theorems from chapter 7. Assume f of C is the maximum of f on the closed interval from A to B. Then if C is strictly between A and B, C has to be a shadow point for f, which means that f of C is less than f of B. Therefore, f of C cannot possibly be a maximum for f on the closed interval from A to B. Therefore, f of A is a max, or f of B is a max, but f of A greater than f of B implies that f of A is the max, so it has to happen at A. And then finally, here's part B. then show that this leads to a contradiction so that in fact we must have f of a equals f of b. Okay, here's my proof. Since f is continuous on the closed interval from a to b, and f of a is greater than f of b, there is a number n in the open interval from f of a to f of b such that f of c is equal to n. That just follows for some c in the open interval from a to b. That follows from the intermediate value theorem. Right? But this contradicts that C is a shadow point of F, therefore the result follows. Okay, and then he does say at the end, within a little note here, this little result known as the rising sun lemma is instrumental in proving several beautiful theorems that do not appear in this book. He refers the reader to page 450, and on page 450, he refers the reader to the book. Well, he refers to the bibliography, and in the bibliography, he makes the reference to the book Real Analysis by Stein and Shikarchi, which is a fantastic book, by the way, one that I own and one that I used when I was studying for my graduate qualification exams for real analysis. But anyway, that's the end of the exercise set for chapter 8. Let me stop the screen share for a second. So I still have to do the appendix for chapter 8 and its a solution and its exercise set. But once we're done with that, we'll be done with chapter 8, and then we can move on to the construction of the real numbers using Dedekind cuts. So I'll see you guys in that video. And until that time, keep learning, everybody.